And so today we have Sascha Grziwa, and he is from the Rhenish Institute for Environmental Research at the University of Cologne. As I say, this is just the first of many visits over the next several years. Our next visitor is coming in actually later this week, Leah Bernabel, and then at the end of this month, we're going to be, I'm blanking on who is coming in. Unique Forest will be coming at the end of this month. And Sascha is going to be talking to us today about upcoming exoplanets in the habitable zone, advances in the detection of exoplanets in the context of the upcoming ESA space mission PLATO. So, Sascha.
Yeah, thank you, Bill. Yes, first, thank you for the opportunity to speak here at the Center for Planetary Systems Habitability. Bill showed me several years ago that this was planned here, and I was really excited because I think yeah, it's very important and good to bring all the different institutes together. I know what I'm talking about because this small institute, I'm working at the University of Cologne, is doing mainly planetary science. So I'm an astronomer, but we are doing planetary science, so many ESA missions probing ionosphere with radio science, and also comets and bodies. So more in this, and I know the difference, and we saw it also last week in this seminar, that there's a difference. Models using 1 point for the atmosphere, for example. So and I have always problems if I want to bring them for planetary science, for ionosphere and also atmosphere into this. And that's why it's really important to get everyone together. Even the language is different sometimes. We saw also, yeah, that last week. A little bit about my work. I'm focusing on detection of planets mainly. So I started, I don't know if everyone, I think I have to do it here. So everyone online can also see it. So here are some exoplanet space missions for detection. I'm doing detection in photometric. So I started 2006, as a younger student, no, not young anymore. I started with Cologne. I looked for a job at the university. And first, I wanted to yes, I was assigned for a job at black holes in another part of the institute or another institute. This did not work out. The budget was cut, and I was the one, yeah, who fell out before I just started. So I looked for another job, programming, everything. So there was this opportunity, I think mid-2006, Cologne. This was an ESA, French, CNES space mission detecting exoplanets. Luckily, it was more about rotation and astroseismology first, but then changed after the first exoplanet was found in 1995. It changed to also detection mission, and therefore it was in advance of Kepler, which everyone from Kepler was not so lucky about. So we were a little bit earlier with this mission, and my duty was to program one of the detection pipelines for Cologne. We had several ones there and programmed it. This was a small mission, a 30-centimeter telescope, so not that large, of course, not even in the vicinity of Kepler. It had but what is important, it has a 120 days baseline for observation. So you mainly say you need 3 transits to detect an exoplanet. So it was about 40 days orbital period possible if you need 3 transits. We did, after all, of course, it was a small telescope. We detected from 2006 to end of 2006, let's say that, until 2014 when it failed. We detected 37 planets. This does not sound a lot if you compare this to the nearly 3,000 confirmed planet of Kepler, but at this time it was a big thing. And we had, of course, some more Jupiters first. We were the first ones who had the radius really precise, and we found the first rocky planet, Corot 7b, which was a super Earth on a very small orbit. And at this times, remembering that was really critical, because the question always is, do you put, so to at this time to detect this, the mass of this planet with radial velocity, after we have this detection, and this is a small telescope, so we are really at the noise level, so at the point what we can detect. And the question was, shall we put all our radial velocity at this observation time, at this time, into this into this one candidate, maybe, or shall we detect other planets? And we, after long discussions, we went for this small planet, and luckily we could confirm, and later on also Cologne 7c. So this was in 2009, even, and then of course, so I worked here in the detection, and then Kepler, when Kepler was launched in 2009, even of course this had a much longer baseline of 1,600 days. You will later hear why I'm talking about baseline so much. Yeah, until 2014, and it was a large haul of exoplanets detected and confirmed. Also many, of course, were also, so let's say at the Cologne times we said for confirmation, if we have radius and mass, which means detection by photometric observation, and afterwards radial velocity measurements. Of course, for so many planets, it was not so easy for Kepler. So at this, starting with this time, we are talking about, and I will talking about characterization, fully characterization. Of course, it's not fully, but fully characterization of exoplanets, so that you have mass and radius, later more of this. So there were, of course, many rocky planets detected, 2,700, I checked this morning, 2,778 confirmed planets, not all with mass, so not all followed up with radial velocity. Only check. And starting with 2014, everyone knows, I guess, then the mission now called K2, because of the failure of 2 gyroscopes, was then yeah, had only a baseline of 75 days, but brought also a lot of planets. Yeah, and starting with this K2, we will see later, we also started our Casperin collaboration, where we'll talk about. This is the connection here with McDonald, or where we started to get connected. Okay, and nowadays, of course, we have TESS. Of course, TESS is ongoing and will go on forever, hopefully. No, the consumables are very, so yeah, the needed consumables are very low, so we can go a long way. Until now, 385 planets were confirmed from TESS. Yeah, and it has a, which is funny, has a baseline of 27 to 350 days. But as you can see here in the lower part, let's say most of the candidates or most of the observation is about 27 or 30 days. So I would say, beside some here in the polar region, or when I go down to the southern poles, most of the planets or baseline is 37 days. Of course, they will come back after 2 years. So northern fields, southern fields, they go around. I think you are familiar with this. Yeah, we go back, but the gaps are so large that this does not have so much. So there are some detections in this, but I would say most of the planets they detect are about 30 days. We are also with our Casperin team working, following up many targets of TESS. I come to this later. Cheops is a mission, it's a small mission, but I think it's a good idea. It's a little bit different from all the observing mission, but I think this is the future. We will see, because this is a small mission, although a 30-centimeter telescope, but this is not doing a survey, so it does not take photos of the large field of view, but only looks at one star at once. So the advantage of this is, of course, you don't need a very large telescope, and it has a good observation of one target. This is, of course, to follow up with planets found by radial velocity or from other missions. So you can renew, so get additional transits, renew ephemeridis, and therefore get the radius from radial velocity planets. This is very nice, and I was also able to do some observations we found with this transits for a third Neptune-sized planet in one of the systems, because we could use these transits. We calculated and were able to confirm this transit. So vice versa as you usually get. Yeah, and then PLATO, not so much here. This launch is foreseen for the end of 2026. I will of course come to that later. Yeah. Some simple statistics. This is really simple. And I don't want to overwhelm it orbit against radius, whatever. It's only a count, only histogram of all exoplanets. I checked this yesterday. All exoplanets, and this is here not the orbital period, which I mostly work with, but with the semi-major axis, of course. This depends then on the star also. But as you can see here, these are all exoplanets for now, with their major semi-major axis. Of course, this goes a little bit out more detected, and as you can see, this dips at 0.05 AU. If you look for Mercury, I think you are familiar with this, that's 0.4 AU. So everything we see here, and we have the same with TESS. Also, I try to do the same scale. It's also peaks at 0.05 AU. And as you see, this is very different from our solar system. I think you know, but it seems that planetary systems are normally completely different. They are all, or most of them, are in the range inside Mercury, very compact. I think you know. But the question of this is, of course, is this because they are built like that, so it's completely different from our solar system, or is this because we don't see them? That's why I go to the baselines also, because as you saw, we have a lot of different missions with small baseline. If you want to find the second Earth, so a planet in a habitable zone around the solar-like star. Short recapture. I don't know if everyone is familiar. There are two very famous methods which work very well. The transit method, which is used by the space telescopes. They use the orbital period. Therefore, because of the periodicity of the transits, if it goes in front of the star, you can calculate the orbital period if it's periodic. And of course, from this, and if you know the star, the distance, you have the inclination more or less of the system, because more than about 5 degrees, then the transit does not go in front of the star. And of course, you're more familiar, I think, with the radial velocity method here, as students also at McDonald. There you measure the shifting of the of the spectrum, and you get the orbital period. Of course, of this with the sinusoidal shift, and of course the mass, not the real mass with it alone, but the mass m sine I, because you only, of course, see you see only the shifting in the observation line regarding also the inclination of the system. But of course, if you combine this with the transit method, there you know the inclinations, you will get a more precise mass. And of course, most important, I mean, it seems simple, but I think you know, most important, you get the true mass, you get the radius, and therefore the mean density. And this is of course key for the planets. So coming to the advantages of the different methods, you have here in red the transit method, and in blue the radial velocity method. And here you have the m sine I, so the mass with the inclination of the planets in logarithmic scale, and also in a logarithmic scale the distance from the star in AU. So here you can see the Earth, Mars, Venus, Mars, and Mercury, and here larger planets. And as you can see, these planets of our solar system are, let's say, below the most detected planets we have here. So transiting planets very near to the star, the super Earths, and also the hot Jupiters, of course. Also with the first one, and of course here for radial velocity, further out, of course, but then only for larger planets, of course, because you need a mass to detect them. Otherwise, they are too small to be detected by radial velocity. Then you have direct imaging, but direct imaging is very, very special because we have this only in the disk. There you can go further out, of course, or you have to go further out for this. But yeah, you probably don't find planet in the habitable zone there too early. And the microlensing planets, I will not forget, but these are single events. If there's a microlens in front and the star passes, so you had a single transit, most of them not repeatable, and so very complicated to use this. So this is the situation we have, more or less. And as you can see, our solar system planets are not so much in the vicinity what we did at the moment. Short recap of Casprint. Casprint we founded, and it's important because several institutes so for us in Europe, or for us in Germany, for example, after Cologne, we were paid for Cologne, and of course for Kepler we did not get paid. So it was difficult to do all the missions, but we needed some expertise of all the fields. For example, I was doing detection, and of course when I go, let's say to ESO, want some observation time for follow-up, they would laugh at me or something. I came with my candidates, and what expertise did I have? So we combined all our several teams in Europe and also in the US and Japan. So as you can see here, some of the teams, and we put in expertise in detection. So we had several detection pipelines. We started to use MK2 also for the correction. We had limited photometry and lucky imaging, and of course radial velocity measurements for moderate precision. And of course we were able to write a lot of proposals. We had a lot of ESO proposals for HARPS North, large programs, even in last years, and also Espresso, which we could use to confirm the planets and get the mass. This was not that bad. I calculated, I don't want to do too much about this, but I calculated we had some about, I think, until now, the Casprint consortium had published about 19, I think nowadays it's about 19 planets, something like that. So not always there's this Casprint in front, so you don't find it sometimes, but it's something about 19 planets in the last years, starting with K2. And TESS now. Yeah, and I think it's very successful. Especially, of course, this brought us all together. So we were, at the beginning, we were 2 teams. And in the Canarian Islands, Hans Deek, one collaborator, said there were 2 teams at the ERC in Tenerife. They said, why don't we join? And this brought us all together, also with the US collaborators. And yeah, this was the starting point for all the collaborations we have. I have with Bill and Mike, for example. So it brings many people together. And this also is key in Europe, but I think it's the same in the US, to bring all these people together to get also some funding, some extra funding. And this was, as Bill mentioned, our ExoWorld exchange program. So this also brings together, it's always the same, detection, characterization, of course, confirmation, statistics. So I'm leading the statistics package, and of course habitability at the end. That's why I'm here. So this is the main context. And this program does not fund observations or something like that, but it does fund exchange, mainly also for students. And we were able to get 117 person month. So at all, about 120 person month over the next 4 years. This started in February. Yes, in February we started with these different detection programs. And as you can see here from the proposal, this is the exchange. Here is the University of Texas coming. There's an exchange about observation. I said here, for example, Judith Court coming, and also from DLR Berlin, and also from us. We have also included, this was also needed, institute in Slovenia, which has machine learning. So this is also one main context for the detection. So we are working on different pipelines in this context for machine learning. And yeah, we also try to do statistics with it. I'm not sure if the sample is large enough, but there in Slovenia, the institute is very, very good at machine learning. They're not even involved until now into astronomy, so we learn from each other, but it looks very good. And of course, atmospheres is also part of this. So after this, coming back to the diagrams, the question is, how shall we overcome this smaller baselines? And I have two things I want to show. First of all, single transits, and second, missions with longer baselines. So first of all, single transits. Single transits are not single transiting planets like in microlensing, but in general, single transits are, yeah, you have sometimes single transits, which you also sometimes also detect because yeah, there are gaps in the light curve, or the baseline of the mission is too short. So this doesn't mean that this only transits once, but you don't have the data for this. And the main problem is that the most detection algorithms use this periodicity. This makes it really easy also going down into the noise level, which you don't have here. You only have the shape of the transit. This makes it much more complicated. And several years ago, I proposed for the German Deutsche Forschungsgemeinschaft, I proposed simple calculations. So what I've done is I took the detections per period of Kepler, K2, and TESS. Of course, they are different. And of course, it's obvious Kepler had many more detections for larger periods than K2 or TESS. Then I tried to calibrate this to the same numbers for 10 days and checked and calculated this for the larger periods. Of course, this is the assumption that, of course, it's not, the fields are not the same, but more or less you can say, which it shows also at the beginning, that the detections of the missions for the different periods, you can compare. And it's obvious, of course, that the number of detections for larger periods depend more or less on the baseline of the mission. But this is not the key thing. After this, let's say it's more or less simple. If you have now here this, let's say, calibrated for 10 days and have the detections of, let's say, at 30 or 40 or 50 days, for example, in TESS, which of course goes down because of the baseline, and you calculate, and you can do this also by cutting Kepler light curves in smaller pieces, then you have the same idea. And we run our pipeline, detection pipeline, on all this data. and calculated how many detections are missing because of the periodicity. And then it's simple for every period. You have the simple detection and you have a probability. Let's say you have 30-day long period light curves, of course, and you can calculate easily for a 50-day orbit, what's the probability that you have a single transit that you detect here. And the numbers you can get together. I don't have the here, I don't here, of course I have it, but here I have not bring in too many numbers, but you can say at this time, 2019, for example, that it shows that there are obviously 400 single transits should be hidden in TESS. And if you check, there are not so many single transits detected. From one to another, you found something, especially if it's very deep, especially if you do radial velocity in a system and you have another one, then of course you check the light curve very, very carefully, and then yeah, you sometimes find something. There are also a few, but not 400. And even more interesting, of course, when you now take the Kepler light curves with this 1,600 days baseline, of course, there are also single transit there, and there's a probability that you also get about hundreds of transits. But you would only find them, or I think the main transit known has the depth of Jupiter. So this is easy to find, but they are non-Earth-like or even Neptune planets. So, but the thing is, what you think, well, yeah, you have the single transit, what shall we do? You have not enough data to get also the mass and the radius of it. There is, of course, a chance calculating the orbital period from the transit duration. Makes sense. You have the speed. So the length of transit is calculated with the, of course, the speed of the planet in front of the star. And of course, this is with Kepler third law. And if you, yeah, of course, if you're using circular orbits in an assumption, and then you get, of course, a linear correlation between the period and the transit duration. And here, here you see it, and if you take of course, the mass of the star into account, mainly, you get a more or less a solution for the period for every transit duration, and you can say roundabout, it's a little bit of discussion, around about 10% error you have with the calculation of the orbital period. Of course, this is not perfect.
Sascha,
Yeah.
does that include the impact parameter?
Sorry.
Does that include the impact parameter?
I think here it's simple. Here it's more simple. It's including more or less that this is also included in the spread because you don't have this from the single
Because that affects the transit duration.
That affects the transit duration, that's correct. But yeah, in this formula I'm using, I mean for calculating at the end for the transit, I use innermost. This is a more complex program which also uses this impact parameter. Of course, you get this more V-shaped transit, and of course from this you can more or less calculate. So it's a Monte Carlo simulation to include everything, and then you get these results. In this simple calculation, of course, it's not included. It's only to show it. But at the end, this is also complete. But this is not included for the detection because it takes several hours per planet to calculate everything there. That gets more precise results. So and then of course, if you have these found this transit and from the duration, you have an idea of the period plus in this 10% error bars. What can you do with this? Well, I showed you the Cheops mission, for example, which can check for a single transit, and we have done this. Luckily, so if you're lucky with your plus minus 10%, yeah, then you maybe have the second transit, and this helps a lot. You can also do radial velocity, of course, and fit this together with the calculation. Of course, there is 10% is a large error. And there's a lot of discussion, especially for long period planets, if it's a good idea to spend a lot of observation time for radial velocity. But it can be done. If you have a ongoing mission, of course, you maybe think about Kepler, for example. I know here's PLATO, but I come to this in a moment. Think about Kepler. You have this mission, and you like Kepler, long kept, and you get 1/4. The second one, then you find a single transit, and you can concentrate on this mission that you prioritize, for example, for the second transit, which is coming later, or you can start radial velocity follow-up even then. And of course, you can do better statistics even with this. So, yeah, we'll go over this. This is how it works. It's denoises the light curve, has a detection for the ingress and egress. And at the end, I use periodic transit, but only with the sample. So here are gaps included, as you can see. This is only to get, we are developing this only to get a larger number of transits. But this detection algorithm does not take the period into account. So it's not phase folding or anything else. And then we check the duration, because not every duration makes sense, especially with the star. And then we fit a Mundell-Argol. So this is this kind of typical transit shape with limb darkening and everything to it. And this first, and as you can see, for example, here is a detection. This is even without filtering. This is a very active star, as you can see. And the most important thing is that this the variation of the star has not the same period than the transit. As you can see, slightly it shifts slowly through this. Yeah, here you can see it at the end through this. Yeah, to the minimum, for example. And this is very difficult if you don't filter this. For example, you cannot detect this because if you phase fold this, it smears completely out because of this second period. But here with this, for example, it works very well. I'm getting late. Sorry. So yeah. So with our pipeline, we are now, let's say, we can detect Neptunes, yeah, and we want to go down to super Earth because this is where we don't have so many. So yeah, we are rejecting false positives. Of course, you have a list of ingress and egress, and you do some calculations, and we reduce this with many models, and afterwards, when we have separated this, we analyze the single transit and get all the data. It's independent from gaps, resolution, also variability. The good thing is that also what I call quasi-periodic transit. So if you have transit time variations, I'm not sure, but if you have in a multi-planet system orbital ratio in very special cases, then the transit is shifted time by time, because of the influence of another large body. And these are sometimes difficult to detect. And even this is not a problem for a pipeline which looks for single transits, also transit from circumbinary planets, which are a little bit odd, can be detected. This thing. And the good thing is this also works on periodic transits, and it does not, and it scales linearly with the baseline. So if you have a longer baseline, and do this phase folding, you usually do, it takes a lot of computation power, and this is not needed here. So it looks that it's very fast and can also, yeah, add it as an additional pipeline. I would not say it you can use it only, but in conjunction with usual pipeline, it can be used very effectively. I don't know. There's shape fine. Okay, nothing. So now come to the point. I think most of you are waiting. Okay, the PLATO satellite mission, because there, of course, at the end, the single transit is not a solution at all. So we need more, or we need maybe another or more missions which have longer baselines. And this is, yeah, and therefore ESA is planning, or ESA is developing PLATO, where I'm working on. Thanks to the primary investigator Heike Rauer, she gave me some of the slides. No, it does not want to work. Here. Okay, this is the these are the ESA space mission Cheops I told you. Of course, James Webb is not an ESA mission; it's a NASA mission with ESA participation. But we have done some instruments and the launcher. I don't know why they show it always. And then there's PLATO. This is this is the next survey, and maybe it's the last survey. I don't know exactly, because I don't know exactly how many surveys are planned. Because these Cheops missions, we have now this coverage also for a long time. We need more, of course, statistics, but I think this is one of the last ones, I guess. And then, yeah, I think Ariel is planned for 2028, which is studying of atmosphere. There's a sample of exoplanets selected or will be selected, and these are studied. Yeah. So, as I said, most important, the mass radius ratio. As you see in all the studies, this is key for what kind of planet you have, of course. And here you see mass against the radius, this diagram. I think you know this. Here's more or less the iron core thing, also here. And here the silicate ones, and here you get to the water planets, and even more with larger atmosphere. Also very important, atmosphere. I get this in conflict all the time with my colleagues from planetary science. Atmosphere means everything but the core. So if you have a Jupiter, atmosphere means not this small, tiny atmosphere, maybe, until 1 hour, how it's defined. I know it's very complicated, but atmosphere for astronomers, because we cannot see anything else. It's everything except the core. Very important, also for Neptune. So as said, it's key. Here also the planets from our solar system, some detection. And of course, we want to have these mass radius. And this does not only include rocky planets. Here you see hot Jupiters. Here, so that's why it's spread. Hot Jupiters, cold Jupiters, and this goes up to brown dwarfs and stellar objects, of course. And this is also something we want to know, but especially, of course, for the small planets. And yeah, and PLATO shall detect planets around solar-like stars up to 1 AU orbital period. So really the second Earth. Characterize them with mass and radius. So this does not mean it's not only a mission where we have photometry and have the detection. It has also a large follow-up program also included. And of course, it showed also the planet occurrence rate here from Kepler, and here also collected together different studies. And the current estimate for Earth-like planets is, this varies from a few percent up to, so let's say 5 up to 100%. So we even don't know how many solar-like planets in the habitable zone around the solar-like stars are there. And if you check here, planets with masses lower than 15 Earth mass and radius lower than 10. As you can see here, you can see here's the stellar mass this time. So this gives you knowledge about if it's an M star, K dwarf, or G-type star. And here's the habitable zone, depending. Here's the distance, depending on the, of course, on the stellar mass and the flux of the star. And when you then go down to planets where you know the mass, where you know the mass by 10%, on the radius by 5%, it's even less. There are not that many. Here, our planets in our solar system. So until now, we have no terrestrial planet around solar-like star, or less, you can say. I know Kepler wanted to find it, and there was also a good chance, but unluckily the stars are not bright enough, and I think we're not bright enough for this. And I think this is also the key for the PLATO mission, because this is the part where PLATO will take place. So as I told you, we are looking for potential habitable planets which evolve like planet. And this is key, of course, to get also insights in comparison to the solar system. So plate tectonics, secondary atmosphere. But for this, we have to characterize, detect small planets, determine their age, and characterize the host stars. Because we always say, if you don't know your host star, you don't know about your planet. Because especially for radius, you have a ratio. So for radius, you need the radius of the star. Then you have the radius of the planet. And it's the same with everything else. So, coming to the science objectives from PLATO. So, as said, the radius and mass is the key. And it's planned, or let's say the requirements are that our sample of G-type stars with a magnitude smaller than 10 and a little bit less constrained for a magnitude of 11 is that we find the radius or detect the planets and characterize them with radius with an error of 3% or 5% for 11 magnitude, and the mass with 10%. So this is included, and very important, the age. So we have astroseismology in this mission, and we want to characterize the age of the stars with 10%. This is important for architecture formation and evolution of the systems. Yeah, as said. Of course, we also want to identify good targets for spectroscopic follow-up and atmosphere. We want to know more about the internal structure of the stars and the planets. And there's also additional planetary science plans. So exomoons, planets around the dwarf stars, and radio studies, also atmosphere. So it's not only the detection of the space telescope, which is meant, but also together with astroseismology and dedicated ground-based observation follow-up, which is also discussed. This should be also come together to get tables of planets with all the parameters to get more in the evolution of the planets, systems, and everything. So coming to the mission. It's a M-class ESA mission, and it should do high precision photometry for magnitudes from 4 to 11 for the main sample, for the more precise sample, and there are also another sample up to 13 magnitude. It will have a precision, or the requirements say, hopefully it's even higher, of 50 ppm per hour for M magnitude 11 class star. And yeah, as you see here, this is a multi-telescope approach of 26 cameras planned. This means we have a 2 billion pixel CCD. And yeah, it's is it here or not in the next? Yeah, and it's a square centimeter size of square meters of 6,600 square centimeters, which is 2 times Gaia, and will be the largest telescope of the largest CCD flown in space to date.
That we know of.
That we know of. Yeah, yeah. There are rumors about some military mission which maybe have larger CCDs. Yes. But with these cameras, yeah, it's good. And of course, it will sit in the Lagrange point, L2. The launch is foreseen, as said, in 26. It will be rotated 90 degrees all 3 months. So there's a small gap. But of course, we have this also with Kepler and every mission. The consumables are defined for 8.5 years. So, as said, the cameras are not that large, 12 centimeter aperture. Yeah, range I told up to 13 magnitudes. And of course, the key of this mission is that we have a large field of view. So the field of view, I hate these, it's 2,132 square degree, but I cannot work with this in comparison to Kepler, but it's 49 by 49 degrees. So it's really a large field. You have an overlap. Here are the cameras. You have an overlap. So in the center, you have 24 cameras at the same point. So you can use this technique also to enhance your photometry. And the lowest are 6 cameras for the outer part. The pixel scale is 15 arc seconds per pixel. I want to go to this fast. And we have 24 normal cameras, which have a cadence of 25 seconds per picture. And we have 2 fast cameras. These are more red or blue. So they have filters. And they have a cadence of 2.5. These are even for the brighter targets for the photometry. So this is a high number of points for our light curves, we hope. Don't know why it. Okay. Here, the field of view in comparison. Well, coming first to the observing strategy. The baseline operation is 4 years. And then, of course, because of the consumables and everything, we, of course, hope that we get extension, as always. The nominal mission will be 2 long pointings of 2 years. And there are alternative possibilities afterwards to have a long 3 years pointing and a step and stare at different locations of 2 months each, but also a very long pointing of 4 years. This is not decided. This will be decided short before the mission. But you can guess, of course, that also because of TESS, it goes more in the direction of long pointing than in step and stare. But it's not decided. Yeah, we hope for an extension, of course. And as to show you, we have the possibility. So here's the envelope we can choose from because of the parameters of the orbit of the telescope. And the Lagrange point. This is the field of view. Here, this is the old Corot field. I don't know if anyone knows these small things. And this is the Kepler field. And these are the several K2 fields here. And okay, I think this comparison shows it. We have a really large field of view, but this is because we are going to the brighter stars. And I think this is key, of course, that we find really after 2 years, 3 years, 4 years, that we find really Earth-like planet around the star, Sun-like star. So hopefully, yeah, there are enough stars, bright stars in this large field. So 2 possibilities. As I'm not, but I saw it on the ESA webpage for the first mission operation plane. So I think it's official. The southern field is selected. There are different, of course, different things taken into account, but one of the things is the radial velocity follow-up. And because ESO is in the southern part, there was a high probability that this field is chosen first. But it is also planned to overlap with the Kepler field. Yeah, there's complementary signs. So on this, I don't see anything, but yeah. There's coming. Okay, of course, there's also complement. I don't know why.
This happened the other day to another speaker.
Yeah.
There's something about.
Yeah. But
Go on.
So it was earlier for the other speaker. It says that my time is over, I guess. Now we started late. Okay, there's also. I have to talk faster. I see it when it comes back. No, but there's I mean, there's nothing, not so much, of course. There's complement.
It's going on. I'm super okay.
Yeah, it looks. I don't know. I don't know. My time is over. No, there's a lot of complementary signs, of course, circumambulatory planets, rings, exomoons, everything planned. Of course, a lot of planets around young and evolved stars, galactic ecology, of course, clusters, a lot of astroseismology. This is really part of the mission, not only for the age. Binaries and everything. And there's a guest observer program, which is 8% of the science data rate. Now it goes away. This was the 8%. No, but there's a large guest observer program, and everyone wants, is look for, This is the structural model. So I saw it even also a few months ago. These are not the real cameras. The cameras are tested now overall Europe. This is really because I'm working on the testing or checking if the requirements are met. And this is a lot. Yeah, there's many cameras, many CCDs, and many stuff to keep track of. But the structural model is now tested, completely filled, and now the cameras which are tested and qualified are now built in. A lot to do, but yeah, we hope this will be a great mission and give a lot of data for everyone. Thank you.
Okay, thank you. Okay, for those of you on Zoom who would like to ask a question, either raise your hand or put it in chat, and we will get your question. Just as somebody who has spent a large number of years as part of the Kepler mission, I must say that looking at PLATO, I'm very envious and heartily terrified of the technical challenges. Mike.
Thanks, Sascha. I'm a little bit surprised about this mass uncertainty criterion or requirement of 10% for an Earth-sized planet in the habitable zone of a 10th magnitude sun-like star.
Yeah.
Does this mean like one will have that mass uncertainty?
No,
For all of them.
For all of them.
How?
So we have a large GOP. I'm not part of the GOP. I'm part of the consortium, so the scientific consortium in different places, but more in detection, unusual transits and everything. I'm not part of the GOP. And at the end, you have to ask Stefan Hudley with this. No, but it's planned really a large program, even the very large telescope. We have some guaranteed time, let's say it that way.
But even if you use a space, so you would need a lot of data to get the signal of
I mean, there's a
talking 10 centimeters a second.
There's a
10%.
Yeah, there's a sample. Of course, there's of course these there are different samples in the catalogue. Of course, there is a catalogue. There's even a very large team working on this catalogue. You can say Sirius is out of the way. We had this discussion even because of course we have a lot of contamination also from very bright stars. So we have to take some very bright ones out of the way. But yeah, we have, so this is not in this talk, but I think it's not secret. The calculations say that we maybe find 30 to 50 in the main sample, and that we find 30 to 50 Earth around solar-like stars in this thing. So for this, of course, and there is a main sample. Don't have the numbers now. Of course, we observe in one field we observe something about 300 to 400,000 stars. So we will check all of them, and of course, not all will. So we don't guarantee that we get for all the planets found there all the masses with 10%, because of course we don't have this radial velocity. But for the main sample calculated, for the best ones, we will try to get 10% mass precision with age, of course.
So not for all of them, just for
not for all, not the main sample, but which is some 1,000 stars. I think it's a large follow-up program, which is under development at the moment.
Any other questions? Anything online?
Let me see. Sorry, I mean, this.
Not seeing any hands raised or anything in the chat. So what did you say was the expected mission lifetime?
As always, it's from 8 point, and the consumerables are 8.5 years, hopefully.
And that's the limiting, expected to be the limiting factors, basically.
Yeah, but of course you never know. But for example, because we have this overlap for the cameras, if one camera fails, for example, or one CCD fails, luckily then you work with splendid files. Of course, the risk is even higher. There's also something to take into account. We have so many cameras, so many CCDs, so many things can happen. But in general, so we have some spare. Yeah, maybe at the end of life, of course, there are calculations. I guess it's the same for Kepler. A lot of calculations about how the lifetime is from CCD and everything. But it's not so the lifetime of the telescope should be 8.5. You never know.
And what was the mission cost?
feel like that's last time.
Okay.
That's
Okay, well,
yeah, okay.
Okay,
I can tell you.
thanks. Yeah.